Last time we started deriving why backpropagation is the way it is, and I did a whole bunch of math, and then my video encoder crashed while encoding the program and the recording was lost, and so that particular lecture won't be posted. That's most unfortunate because mathy things are the very things you need to go back and review the most. That's a shame. Oh well, moving on. I don't have that lecture, but we'll review it as we do it some more. However, I don't want to just review it today. I want to cover instead implementation details. So today I'm going to go over how exactly to code up a neural network, and then we'll circle around back and revisit why we did it that way and why backpropagation is what it is. So there's the plan for today. One thing I want to point out is this view your scores thing that we have where you can go view your scores. If anybody signed up for the class late and you're not on here, please send me an email and I will add you to the list. If you have not learned how to use the system yet, try picking your name and just click log in. That's not going to work for me because that's not my password anymore. But by default, you have the empty password. Some of you haven't figured that out yet. It says it somewhere. I can't remember where. If you don't know your password, it's probably the empty password. You can't check your scores until you change your password. So go log in, then you can check your scores. Please do that because you need to make sure I'm grading you fairly. There's enough students in this class that there's a lot of potential for me to screw up. And if I do, well, it's a lot easier to fix it if it's just a couple of days difference. It's not so great if at the end of the semester you're saying, oh, by the way, you messed up all of my assignments, please fix them, because then partly on your head, right? So please keep track of your scores and stay up to date. Plus, I've got 2 reading assignments scheduled in a row, and I called this one Readings 1, but this one was really Assignment 1, and yet if you click on it, my instructions say, I spent the required amount of time studying Assignment 2, and that gets confusing because people might think it's Readings 2, and now the wording is basically messed up and I shot myself in the foot. So you'll want to check your scores just to make sure I gave you the credit for the one you were trying to communicate to me that you had done. Otherwise, a couple emails might need to be exchanged to sort it out. Please make sure I gave you points where points were due. And if I gave you points where points were not due, you can be an honest person and indicate as much, or at least go do the reading assignment on time, and then it won't matter anyway. There we go. So today is the 6th, which is right here. Valentine's Day is coming up. If you have a significant other, plan to do something. If you have an awesome significant other who says, oh, you don't have to do anything for me, it's a trap. Go do something. You have been warned. That has nothing to do with this class. I'm just telling you, you should get on that. I have some another reading that we're going to do by the end of this week. This one is about, so the first one is a pretty short paper that basically says, hey, look, it's the year 2000 and something, and yet backpropagation, which was invented way back in 1969 or 59 apparently, so long ago, is still rocking the world and breaking records at doing awesome things. And that's just kind of fun to read. This is a really light, easy to read paper. You could skim it pretty quickly. They did their testing with the MNIST data set of handwritten digits. We're going to do our assignment with that too, just because it's an easy toy problem and everybody uses it in neural networks. And so this paper is kind of highly relevant for this assignment that you're doing. The next assignment is a crazy survey paper. And by crazy, I mean it was written by Jürgen Schmidhuber, who is kind of one of the godfathers of deep learning. And if you look at this paper, you'll see that there are about 40 pages of references. Obviously, I don't want you to sit there reading the references. That would be a huge waste of your time. Don't do that. But this paper is the most thorough survey of deep learning I've ever seen in my life. And I figure if you're going to learn about deep learning, you might as well have a basic background of the history of where it came from. By the way, this paper has citations measured in the tens of thousands. It's an extremely cited paper. So basically, because if you say anything about neural networks, you could cite this one, and it probably says it in there somewhere. So good paper to read up on. You won't finish it in the allotted amount of time, so just spend your time kind of trying to get a feel for what's important to you and what's important in deep learning, and skip the parts that feel like they're wasting your time. I don't want you to spend your time reading as though I'm going to test you on, did you catch this detail? I'm not going to test you on details embedded in the reading unless I've emphasized them in class. But I do want you to spend some time, familiarizing yourself with the domain, and hopefully you're interested enough that this stuff is interesting to you. So please read and enjoy. And if you absolutely hate these reading assignments, well, why are you taking a graduate level class, right? I hope it's an enjoyable experience. And if nothing else, you'll learn how to read technical papers. So one of my first memories of being a grad student is they throw these papers at me and I start reading them, and what the heck am I reading? It could have been Greek, right? Do you find that? Well, sorry. I'm going to try to ramp you up so that you can read these papers and understand them, but it's a lot of work, and there's no way to get there if you don't also just try reading them, because you have to it's been said that you never really learn math, you just kind of get comfortable with it. And that's the way it is with academic papers too. You just you get used to words you don't understand, and you get used to technical concepts, and you start learning what to look for. You start to realize how to read these equations. You start to realize how to penetrate an academic paper. So just spend a little time doing it. It's part of the graduate experience. And the more technical papers you read, the more you'll learn how to read them, and then the more you'll get out of them. And if you put in the time, I'm giving you credit. So there's that. Any questions on the reading or checking your grades or any of that stuff? Yes? Oh, is it? Ha! I have assigned you to do something you cannot do. I apologize. I will have to fix that right after class. Thank you for calling that to my attention. But just so that we can point you at it in case I forget to fix it right after class, I won't. But here's my lab wiki. Here's my Dr. Glashler's collection of data sets. Here's the MNIST data. There it is. You could download it from right here, trainandtest.arf. And they are located at uaf46365.ddns.uark.edu/data/MNIST. There you go. There's the link I'm going to update it to when I get around to it. And hopefully that link will work immediately after class. Okay. On that note, actually this is where I want to be. Let's just start talking about this assignment. So I think you guys know how to do reading. Just start a clock, spend some time. And by the way, I do want you to be organized. It's okay if you get through some paragraph and you say to yourself, I have no idea what I just read. And so you go off and you look up terms and you spend some time. If you spend more time on Wikipedia than actually in the paper, okay, do what you need to do to make your time useful, because I really want it to be useful, not just did you go through this miserable experience to get your points, right? There is a point to reading these papers. Okay. So you've already got a layer class. We coded that up for assignment 1. And your layer class has a member variable named activation, which is a vector of double precision floating point values. I'm now asking you to add another one called blame. And We'll initialize that. And we'll add 2 virtual methods to your layer class. So now your layer class will have 3 virtual methods. All layers that we'll implement in this class will be able to activate, backprop, and update gradient. And we'll talk about why and what that means in just a minute. For the Java users, it'll look a bit more like this. But basically, this amounts to copy this, paste it in your code, and you've done it. Any questions so far? Yes?
You didn't specify the type of weight.
Right here. Oh, you're right. It should be a vector. So that should say vec right there. In fact, I'll forget if I don't fix it. So didn't I do that last time? Okay, so I copied my own bug, huh? Backprop. Come on, where is it? This doesn't look right. That's because I'm in assignment 3. That should be vec, not an ampersand because we're in Java. One of them is fixed. And size t should be int. I swear I fixed that. I know I did. Okay. Anyway. Hit refresh. And they're fixed. Yay. Okay. I should go fix that link too. Anyway. Your time, I will fix my link after class. Okay, implement the backprop method in your layer linear class to compute previous blame equals m, by which I mean your weights. I'm not sure why I used the letter m here. I should have used w. I guess because we used m in the last assignment, so m makes sense to you. I put a transpose there, and this asterisk here indicates matrix vector multiplication. How do you know that? Because this is a matrix and this is a vector, so what else are you going to do, right?
So when we're using m,
Yeah.
because our weights contain our b weights as well, we're going to have to make sure that we cut them out. Right?
Good point. In this case, we're going to ignore b. So you're not going to subtract b from this, you're just going to multiply it by m. Why? Because that's what the instructions say to do.
Right.
So yeah, this is not the inverse of what the linear layer does when you activate it.
Well, okay, so we're just going to use weights. I guess I'm confused by this. When if I was to turn the weights into a matrix, wouldn't I get messed up by my b's being at the start of the weight?
Yes. So let's talk about exactly what we're doing. Let this square whoa, that's the wrong screen. There we go. Let this square represent your linear layer such that if x goes in, y comes out. Now, in the previous assignment, you implemented a method named activate. And that's what activate does. It could be titled compute the function, or compute f of x, or predict the output, or something like that. What you're doing is activate is going to take x and compute y, and the formula it uses to do that is y is equal to mx plus b, where mx is matrix vector multiply, and this is a vector-vector addition, and the result is going to be a vector, x is also a vector, and so forth. So we have this activate. Now, you might say activate is going that way. And we're going to implement now a new method called backprop, which goes in the opposite direction. And you might assume that the purpose of backprop is to do the opposite of activate. That is, if you have y, compute x. If you were to assume that, you would be wrong because that's not what we're doing. So the way this is really going to work is, suppose we have computed this y equals mx plus b. So we've computed y hat. Let me draw a little hat on there. Not red. Draw a black hat. Okay. After we have computed y hat, we're then going to assign blame. So we're going to say, how wrong is this y hat? For example, if y hat turned out to be the number 3 and we wanted it to be a 5, because y is actually 5, then the amount of blame we're going to stick on here is 2. And I'm going to use red to indicate blame. And now, because what we actually have is a single layer, there's no reason to pass the blame back, because we only have one layer. So really, there's no need for this backprop concept. We're going to be moving from single layer models to multi-layer models. So our models are now going to look a lot more like this. And just because we can, let's add another one in here. Okay. Now, if we know that this layer bears 2 units of blame, then we would know to take steps. We're going to update the weights in this by some amount proportional to 2, because 2 is going to be how wrong is this layer, and we're going to update the weights by stepping some amount that'll fix those weights. But then we face the question, what to do about these 2 layers, right? They have weights too. How much do we adjust their weights? And you might assume, well, how about we just adjust them all by the same amount? Turns out that doesn't work very well. And it doesn't work because the amount that these layers cause problems for the prediction differ from the amount this layer causes problems for the prediction. So if we do a whole bunch of calculus and we compute the math, turns out that there's some different amount of blame we should assign here. Let's say it comes out to 1.2. And maybe this layer bears 3.1 units of blame. And if we adjust the weights in all of these layers according to how much blame they bear, where blame is some value I'm going to compute that's part of backpropagation that comes out in the calculus, then we're actually stepping in the direction that's most downhill, and this whole thing predicts better predictions faster than if you don't do all of that math. Does that sort of make sense? So the purpose of this backprop method is to say, hey, we know this number. Now we need to compute that number.